As early as January of this year, anomalous weather patterns began breaking record after record, beginning with the heavy snow accumulations in the northern Missouri River Basin, foreshadowing what would become a devastating and crippling year of floods throughout the entire Mississippi River Basin for much of the late winter and early spring. Then, 1 month ahead of schedule, a record-setting tornado season began, featuring some of the most powerful tornado systems in U.S. history, both in number and in force. As summer set in, a string of rare earthquake events erupted across the United States from New York to Colorado and Virginia. And then, shortly thereafter, the north and southeastern United States were hit first with Hurricane Irene, and then later, in a matter of weeks, by Tropical Storm Lee. Now, as we move into the winter months, the record-setting severe weather pattern doesn't appear to be letting up, as we saw in the freak snowstorm that slammed the Northeast in late October, and the record-setting snowicane that just pummeled the western coast of Alaska. Then there's the curious case of Oklahoma, a part of the country that throughout the last year has experienced state of emergency droughts, tornadoes, and floods, and just recently, in the beginning of November, experienced all three simultaneously. In the case of each individual event, approximate explanations for the anomalous behavior have been given, but with many questions left unanswered. As for an explanation for the year as a whole, an explanation for why all of these seemingly different events occurred back to back and sometimes simultaneously in a single year as if part of one system, remains a mystery to the conventional weather and earthquake forecasting methods. But if we take a closer look at the recent events in Oklahoma and combine them with the 200th anniversary of the New Madrid earthquake swarm of December 1811, we find that some light is shed on what may be a driving factor in these mysterious pattern of events. 200 years ago, the region of what is now called the New Madrid Zone experienced a swarm of some of the most powerful earthquakes in recorded history. Beginning on December 16, 1811, the first earthquake struck, measuring somewhere between magnitude 7.2 to 8.2, with its epicenter in northeast Arkansas. At the time, this part of Arkansas was sparsely populated. However, the earthquake's power propagated throughout the entire east coast, knocking down trees and collapsing riverbanks in New Madrid, shaking windows and furniture in Washington, D.C., and is even said to have rung church bells as far as Boston. So far this year, 2011, has been a year of records, particularly for the state of Oklahoma. In February, Oklahoma set its record low temperature of negative 31 degrees, along with the most snow to fall in 24 hours, 27 inches. In May, its highest wind speed was recorded at 150.8 miles per hour, and the most powerful tornado ever recorded in Oklahoma history was recorded this year, along with the largest hail. And just recently, the strongest earthquake in the state's history, a magnitude 5.6, was recorded on November 6th. Now, while many of the symptoms the New Madrid Zone suffered 200 years ago are somewhat similar to the pattern that has broken out in Oklahoma and other parts of the country in the past year, and that the events are totally anomalous to the regular weather patterns, what is more interesting than what is happening on the ground is what is happening with the sun. What appears to be the case is that the sun is in a similar position today in terms of its longer cycles of periodicity as it was 200 years ago, which was called a long solar minimum called the Dalton minimum. Currently, the best estimate of our sun's activity is that it is halfway through cycle 24's approach to solar maximum, a 3 to 4 year period of dense activity in the form of sunspots, solar flares, and other newly discovered behavior, all part of a regular, roughly 11-year solar cycle. These cycles, based off of the waxing and waning of highly polarized blemishes appearing on the surface of the sun, called sunspots, have been observed for thousands of years, beginning in early China, but it is only the most recent 400 years of sunspots that we have a reliable record of. What is interesting is when you look at a mapping of the sunspot activity since 1755, while the 11-year cycles predominate, other cycles begin to make themselves evident as well. Take cycles 5 and 6, which began right around the turn of the century, and compare them with the cycle 23 and our current cycle 24. But periodicities show up in more than sunspots alone. For example, here is a map put together by David Archibald on the emission of radio waves from the sun, what is called the F10.7 flux. Here you can see a similar minimum trajectory in cycle 24's activity relative to cycles 18 through 24. Proof that there are many ways to speak the language of the sun. In 1976, John Eddy made a forecast of the sun's behavior, not into the future, but through reverse engineering, mapping out the last 1,000 years of the sun's activity by combining radiocarbon dating of tree growth, frequency of auroral occurrences, ancient manuscripts, old literature, and modern data, and came up with a number of potential cycles. Now immediately 2 questions come to mind. What do these periodicities mean for us on Earth? We know nominally that in the recent past these minimums, along with others like the water minimum and the spore minimums, correspond to lower temperatures on Earth, including what was referred to as the 16th century Little Ice Age. But what other effects does this change in solar radiation induce on Earth? The second question is, what are the long-term periodicities that exist in our galactic and extragalactic environment that the sun is responding to? One way to begin to understand what otherwise appear as discrete, strange weather events is to take these phenomena and think of them together as a system and begin mapping them against these larger periodicities that we are a part of beyond our planet and beyond our solar system. But there's also the hard truth that if we want to know more about weather and how it changes over time, there's no way we're going to do it sitting here on one planet. Our knowledge is bounded by our exploration. Therefore, if we wish to push the limits of our current knowledge, which allows us to be caught off guard by powerful earthquakes, or cannot explain the kinds of severe weather patterns we've experienced so far this year, we're going to have to expand our horizons.